Good morning, everyone. Thanks to the organizing committee for giving me the opportunity to introduce the speaker of the first session, the role of mechanical design in MEMS by Dr. Ananthasuresh. Dr. G.K. Ananthasuresh is a professor at Department of Mechanical Engineering in Indian Institute of Science, Bangalore. He is best known for his work in areas of topology optimization, compliant mechanism, and micro-electromechanical systems. He has done B.Tech in Mechanical Engineering from IIT Chennai in May 1989. He has done MS in Mechanical Engineering from University of Toledo in March 1991. He has done a PhD in Mechanical Engineering from University of Michigan in December 1994. He was a postdoctorate research associate at Microsystem Technology Laboratories, Electrical Engineering and Computer Science Department from MIT, Cambridge, since February 1995 to September 1996. He is a recipient of prestigious Shanti Swarup Bhatnagar Award in 2010 for Engineering Sciences. He has published 89 journal articles, 7 books, and 93 conference papers, and has more than 15 patents on his name. I welcome Dr. Ananthasuresh from the team SPCE. Sir, you can start the session. Thank you.
Okay, thank you. Good morning.
Sir, sorry to interrupt. Just we will have 5 minutes wait because schedule we have already finished ahead of like 10:30, and 10:30 some participants may join for the session directly. So
okay.
5 minutes we will wait. By that time you can share your PPT and make the arrangement.
Sure, we'll do that.
Start after 5 minutes maybe.
Yeah.
That will be good for participants for joining late.
Sir, let the participant join and during that time let the participants may introduce themselves so that we can have a very good kind of a team while learning. And
yeah, that is a great idea. So if 5 minutes.
So let every participant will introduce himself or herself. I'm also one of the participants.
Yeah,
I'm Dr. Santosh Rane, working in Sardar Patel College of Engineering as Dean Academics and faculty in Department of Mechanical Engineering. And I'm very happy to join this program. I'm very happy to learn the new thing. This is totally new thing for me, MEMS. I'm very much interested to learn many more things. Thank you. Next participant, AP Gargade. So please introduce. Participants, please introduce as per the name. Yeah. AP Gargade, you can introduce yourself. Let the people join, and at the right time we can start. Okay.
Hello, sir. Good morning, sir.
Hello. Good morning.
Yes, good morning, sir. I'm Professor Abhijit Singhe, working as an assistant professor from Tatasaheb Kore Institute of Engineering, Kolhapur, Maharashtra.
Nice.
Okay, welcome, sir.
Hello. Hello, sir. Hello, sir.
Yes.
Hello, sir. Myself, Professor Vishnu Sonone from All India Sri Shivaji Memorial Society, College of Engineering, Pune, Assistant Professor in Production Engineering. Sir, I am very, very eager to learn these micro-electromechanical systems. And here you organized this from the Sardar Patel College of Engineering. And this is the opportunity to me. Thank you, sir.
Welcome.
Welcome, sir. Welcome.
Thank you, sir.
Hello.
Good morning.
Yes, sir.
Good morning, sir. This is Chetan Somani from MS University of Baroda. I'm assistant professor in mechanical engineering, and I'm eager to learn about MEMS. And also congratulate Dr. Kiran Bhole and his team for organizing such a good training program. Thank you.
Welcome, Professor Chetan.
Good morning, sir. Am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Good morning, sir. Myself Mohit Jain from Manipal University, Jaipur. I am here an assistant professor in Department of Mechatronics, and I am very happy to join this course, and it will be exciting to get this course done. Thank you.
Hello, sir. Hello.
Yep. Yes, you are audible.
Myself, Sushant Karnataka Jane from IISc College, assistant professor in mechanical. Hello. IISc College of Engineering. Thank you, sir.
Good morning, sir. Myself, MK Jawahar. I am working as assistant professor in Sri Sastha Institute of Engineering and Technology, Chennai. I am doing my PhD work in thermal engineering area. So I am eager to learn for micro electromechanical systems, sir. Thank you.
Okay, welcome, sir.
Thank you. Welcome.
Any participants from the northern side of the India?
Yeah. Please introduce yourself.
Hello, I'm Dr. Hello, hi, I'm Dr. R. Vimal. I'm from Assistant College of Engineering. I'm working as an associate professor here. I do some of my research in MEMS, so I wanted to participate in this FDP program. Thank you.
Hello.
Hello, everyone. Hello. Yeah.
Yeah. You are audible.
Hello. Hello.
Yes, you are audible.
Good morning, sir. Myself, Ankit Oza, Dr. Ankit Oza. I am from Gandhinagar, Gujarat. And I have also worked on the micro machining process. So I hope this workshop will give extensive knowledge in my area. Basically, my research work is involved in fabrication of various micro machining setups for mainly used for MEMS application and other applications. So I saw this Atal course, AICT. So it's a very good course, and I hope I will get extensive knowledge. Thank you, sir.
Okay. Welcome, Professor Ankit.
Yes, sir.
Welcome for the course, sir. Welcome for the course.
Welcome.
Thank you, sir.
Hello.
Hello.
Yeah. Yes, you are audible.
Yeah, this is Pragati Tathe from Maharashtra. Sir, I am working as an assistant professor. Actually, I'm from the ENTC background, but many of my students are preparing for the ISRO exams. So nowadays, some of last 2 to 3 years, ISRO has going to recruit the special intake students from the MEMS technology. So I'm quite interested in MEMS. Actually, I'm not aware about this technology because in our graduation or in our post-graduation program, MEMS is not the syllabus. So I'm quite interested for this workshop.
Hello, sir.
Yes.
Hello, sir. Good morning. I am Anita Jena, and I am a PhD research scholar working on micro nano 3D printing facility, that is Nanoscribe, in Department of Mechanical Engineering, IIT Kharagpur. I really thank you for organizing this FDB and looking forward to learn more about microfabrications for MEMS. Thank you so much.
Thank you. Welcome.
Thank you, sir.
Good morning, sir. This is Esther from the Department of ECE, Assistant College of Engineering, sir. Thank you.
Welcome, madam.
Hello, sir. This is Gulam from Assistant College of Engineering, and I work in the Department of ECE. My area of interest is electromagnetics. MEMS is new to me. I just want to explore what is new in MEMS and how can I accommodate that into my research.
Welcome, sir. Thank you.
Thank you, sir.
Hello, everyone. My name is Charudat Mazde and I am from KKR College of Engineering, Nasik, Maharashtra.
Welcome, Professor Sardar.
Good morning,
Thank
sir.
you.
This is Dr. Srija from Assistant College of Engineering. I have seen talks from Professor ANANTHASUREsh and others whom I know, so I thought I will attend this workshop. Thank you, sir.
Welcome, Srija Madam.
Yes,
Thank
sir.
you.
Good morning,
Hello.
Professor. Good morning, Professor.
Yes, good morning.
I am Suresh Kumar from Government College of Engineering, Srirangam, Tamil Nadu. And I am working in EEE department. Thank you, sir.
Welcome, Professor Suresh Kumar. Thank you for joining the course.
Thank you, ma'am. Thank you, sir.
Good morning, sir. I am Ashok Nakum from Polytechnic, lecturer in Mechanical Engineering Department, Polytechnic, MS University of Baroda, Gujarat.
Okay, welcome
Thank
to the
you, sir.
course, sir. I think
Thank you.
we'll take here now the end of like introduction for the participants. We'll continue that in next sessions. Before the sessions, like we can have interaction. So let us start this session now because it is 10:30 as per our schedule. We shall start now the session. So I request Professor G.K. ANANTHASURESH to start the session.
Yeah, can you hear me?
Yes, sir. Yes, sir. You are audible, sir.
And you can see my screen
sir.
also, I suppose.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. Good morning to all. I first thank the organizers and your college for inviting me to your faculty development program. And I thank Dr. Bhole and Professor Umale and Professor Rane and Professor Murli and all others and all the faculty who have joined this. I'm glad to see such a large number of people joining this FDP. I'm at IISc, as you can see. And I changed the title a little bit, and I will tell you why I chose this particular topic a little later. This work was done with my students, Dhananjay Yadav and Nitish Satyamurthy. Also, my postdoc, Dr. Sudhamshu Shekhar. And this work that I'm presenting was funded by ISRO, Laboratory for Electro-Optics and Systems in Bangalore. And Dr. Giridhar over there in ISRO has worked with us on this work. And since we are having this FDP on MEMS, micro electromechanical systems, I thought I would first start with an overview of the field as I know it. First, MEMS started when people started to build mobile mechanical elements that coexist with microelectronic circuit elements. That is, you have mechanical elements that are integrated in every possible sense of this word with the microelectronic circuits. And that's why they are called initially micro electromechanical systems. But then very soon people realize that it is not just mechanical and electronics that can be integrated onto a chip, like a electronic chip. Now we have MEMS chip. You can do chemical, optical, thermal, anything that you think, acoustic, all kinds of things can be put into MEMS. So the field has exploded. It started, I would say, in late 80s. Now after 40 years, it's almost everywhere. There are lots and lots of microsensors. When we say MEMS, the first thing that anybody would cite as an example would be a microsensor, either a pressure sensor or an accelerometer. And number of sensors are there. In fact, more sensors than probably we need. But then sensors are always needed to control a system and make it perform at its best. Now we have Internet of Things and cyber physical systems for which sensors are really crucial, and MEMS field is playing a big role in those things. And then we have actuators, micro actuators. These are not as many as microsensors. To this, to make the point, in Microsoft Word, if you put microsensor as a single word, it does not complain. Put as the micro actuators, it thinks it's a wrong spelling. It wants to split micro and actuators. That means that micro actuators have not become as widely developed or used as microsensors have been. And that's why I chose the topic of my presentation today, and a micro actuator rather than a micro sensor. And there is also power MEMS. That is, you can generate power on the chip. So basically, you can do many things on a chip today. One of them is generating power. And also, there is this concept of metamaterials. We all know materials. What are metamaterials? Metamaterials are those where, by design, if you control the microstructure or the hierarchical organization of material, any single material that you take, you can create a metamaterial that has interesting properties. And I'll give an example of that. And then there is microfluidics. I'm sure you have talks on microfluidics today, and rest of the course that you have now. People talk about lab on a chip. The entire lab can be on a chip, and that is now well done. There are journals of this name and lots of stuff. Now people are actually talking about medical applications where you can have organ on a chip. You can have lung cells or kidney cells or heart cells on a chip. And then people also want to work on body on a chip now. Not that we'll have human body on a chip, but all kinds of cells of human body can be put on a chip so that we can actually create a body in a chip. Now, I talked about MEMS not being just mechanical electronics today. There is so much of the other fields. You can do body on a chip. And then there are a lot of tools that have been developed using MEMS technology for probing microbiology or nanobiology. There are lots and lots of interesting things that are being done because now you can make tools that are of the size of the cells. The micro, all of you know, is 10⁻⁶ meters. The cells are also of the same size. So you have access to the workshop of nature, that is a biological cell. You can go in and do all kinds of things to it. And it's also really exploding. And now, so far, MEMS have been tethered, meaning that they are fixed to the chip. Now, if you let them go free, make them untethered, let them go wherever they want. And now you have these micro robots. And a lot of work is being done on micro robotics now. And people already envision what can be called hospital inside a body. So we have a surgeon. This is something that Richard Feynman had talked about, maybe half jokingly, that you swallow the surgeon. That is, you swallow the surgeon, right? So basically, you can have little robots that can do surgery inside. You swallow them or inject them inside. Now people are thinking about the entire hospital. There'll be all kinds of things. There'll be nurses, doctors, and medicines and everything that will take care of your body inside. And that's what people imagine today. In fact, if you think about MEMS, the applications are really unlimited. There are so many of them that I cannot cover in a slide. I just wanted to give you this. Also give a sense of what has been done. Let's say our group. Our group is called M2D2, that is Multidisciplinary and Multi-Scale Design and Devices Lab in IISc Mechanical Engineering. We have worked on accelerometer, a dual axis accelerometer, also a cognitive ring. So it's actually a ring that you can see like gold plated, silver plated, but this is actual prototype. That is rendering is actual prototype. If you wear this, you can do gestures and control things around you. And in fact, I've given presentations by wearing this ring where I can change slides by moving my hand like this, right? But then swiping, all these things that have come now, so it's less relevant, but people are thinking about cognitive jewelry. So Tanishq, for example, is really interested in such things in India. And we have made a micro Newton force sensor. So they're all sensors. Like I said, there are lots and lots of sensors. And there are actuators. That's what I want to talk about. In particular, electrothermal actuators, because they provide a larger force than electrostatic actuators. I'm sure in this workshop, somebody would describe electrostatic actuators, the comb drive, for example. But then those things can move themselves. They cannot move something else. When you say an actuator, we want it to have enough force so that it can act on something to move it. Electrothermal actuators actually are capable of doing it because their force is much larger than what electrostatic actuators can provide. And there are also electromagnet actuators, which I'll briefly describe. This particular one is electrothermal actuator. All you have is a bent beam. If you apply voltage, it's going to move. Likewise, over here, you see a folded beam like this that also when you apply electric potential that can deform. And I'll talk more about this. This is actually the topic that I'm going to discuss today, and the role of mechanical design in it. And about this metamaterials. So what is a metamaterial? You have basically a silicon, but then you make some design in it, some slits here, there, right? You get this, and this has the ability to expand when you apply voltage between these 2 points. Like these 2 points and the real device, these 2 points apply potential, is going to move like this. Now turn 90 degrees and put an array of them. And if you look at this block, if you look at normal thermal conductivity, or actually thermal expansion coefficient, you can actually change it, you can enhance it by playing with design. Many material properties can be changed by design, and that's what is metamaterial. You can take any single material and you can get properties of equivalent materials that are different from the base material, just because you are going to design the arrangement. And we also developed a lot of tools for probing biological cells. What you see here is actually a breast cancer cell, MCF7 cell, which will be about 10-15 microns in diameter, and is being held with a micro gripper. As you can see, this is SU8 micro gripper, SU8 polymer. There's a glass pipette just to position it, and this one can actually grasp the cell, single cell, and we do these measurements on single cells to assess various biological, I would say, effects, as well as disease states. And what you see in the bottom here is actually zebrafish embryo being squeezed and it's being released. We can measure viscoelastic behavior of the cells as well, static and viscoelastic and dynamic, all that we can do in a single cell. And then we have also now these micro robots. Micro robots are not anything fancy. You just have few appropriately shaped devices. These are, again, we are using SU8 polymer, and these are free floating ones. What you see here are the cells. These are fibroblasts, and these things can be grown on these micro robots, and then this micro robot can be moved around. What you see here are the coils, electromagnet coils. Again, electromagnet force is also quite high compared to electrostatic force. Now people are moving towards magnetic actuation of micro robots. We have this array of coils and a chip, and these are the little robots that you see, different shaped robots. And one of them I'm showing here, another one showing here, where biological cells can be grown on them, so we can shepherd the cells where we want and do lots of things. These are the ones that go inside the body and set up a hospital inside the body. Okay, so one of the things that we would like to do here is to have these robots, like this video would show, move independently. So here you see there is an array of coils underneath. These are really tiny robots, which is 10 microns in diameter. One is going that way, other is going this way. That's what we would like to do. We would like to be able to control them externally. So body is there, you could apply magnetic field around the body and move these things inside. You can take where you want to take and do what you want to do. So this is the micro robot technology that is ongoing in our lab and many places in the world as well. And we also make these what are called scaffolds for cells. Just like for a building, we have a scaffold. When you want to do tissue engineering or regenerative medicine, you provide scaffold for the biological cells. And here we use micro-electromechanical structures so that we can apply forces and measure forces that are being applied by the cells. Both of those we do. Our eventual goal is to assemble cells which are cultured on these micro robots and make tissue inside the body. There are applications where this is useful, and that is where we are trying to go. So while there are so many different things that MEMS have applications in, but I chose this particular topic, electrothermal bistable switch, and there is a reason for it. And I want to explain that reason. The reason is this person, Dr. Nilesh Mankame, who is an alumnus of your college. He sent me this slide. So as you can see, your college building, I guess, I don't know how old this photograph that he has. And after that, he came to join me at University of Pennsylvania to do his PhD. And he worked on what we call compliant mechanisms, in particular contact-aided compliant mechanisms. Also, there is a hot valve that he developed, and that's actually now commercially used. There are clinical trials happening, and two companies have bought. So Nilesh has that credit. Now he has been working at General Motors in Detroit, Michigan, and he's very well recognized for his work. I want to tell you that one of your students, your college students, has done really well, and he has won some awards there. And I would like to show this particular video that he has sent. Let me just go there. I hope you can tell me if you can hear the sound. Can you hear the sound from the video?
No, sir.
No.
No, sir.
Okay,
No, sir.
that doesn't come. But basically, I would like to play, and then I will explain while it is happening. So these are actually metamaterials. You see, they're normal materials, but now you have some structure in them, and they behave differently from the original material. They say this is based on honeycomb structures. And this is the work of Nilesh Mankame when he's working with the professor at Purdue University. And Nilesh also will come in a minute, so you can see how he looks now. So this is Nilesh Mankame. So this is for energy absorption, and so you can see this metamaterial once when it comes, when Nilesh explains. There are a lot of applications, automotive, aerospace, and this is Nilesh Mankame explaining to us what he has done with these metamaterials. So you can see the structure of these things, right? And they have different properties. Now you can do that at MEMS scale very easily and create the things that you want. So I'll stop here. Yeah, you look at that. Again, that is Nilesh Mankame. And that is bistable, you see. You presses it, and then that goes to other state. You presses it again. Yeah, that stays there, right? So let me stop it here and go back to my presentation. So if there are students, I think we should be inspired by what Dr. Nilesh Mankame has accomplished. And there are many more things that he has done. Now, let me go ahead and explain the last bit that Nilesh showed, which is this bistability. As you can see, the bistability is all around us, in hair clip to binder clip and some bottle caps and eyeglass frames, and everywhere we have bistable things. And you can use them at MEMS scale, which is what we have done. That's why I chose this. Another reason I chose this was that Nilesh's master's thesis was also electrothermal actuators. And his paper is, his title of this paper is Comprehensive Electrothermal Elastic Analysis. And that paper is highly cited now. And I thought it was relevant to talk about your own students' work when I'm presenting at an FDP in your college. What is bistability? If you look at the energy landscape, like it is shown here, right? If there is a minimum here, there are two stable states. If this is potential energy or free energy, in between there is a maximum, which is unstable state. And that's what Nilesh was showing with his hands when he presses. Now, here are various ways. You have bistable arches, a single arch, two arches, three arches, and then a ring, and then something else, and the shells also. So you can use this bistability, which is highly nonlinear behavior, to do useful things. And just to look at what is bistability, I said energy has two valleys and a hill in between. This is energy, potential energy. If I take derivative of this, then you get the force, right? Wherever this is minimum, force will be 0. Maximum also, force is 0. Minimum, again, force is 0. In between, you get this kind of behavior. As you can see, as the displacement increases, force goes up and comes down. Whenever force displacement has a slope that is negative, that is an indication of either snap through or bistability. Snap through, or we are pushing, that itself goes further. You don't have to do. That is the negative spring, so to speak. Positive slope is positive spring, is negative spring. That is, you are pushing, and that will not resist your push, but go in the same direction. That's what happens in between, and then it goes negative for example sometime, and then comes back to the zero position. And this is the nature of the bistable structures. And just to illustrate, you're starting here. Let's say I take a shell which is hinged at the edge of the shell, circular shell. And then as you start applying force over there, there'll be a point, then it start deforming. There'll be a switching point. After that, even if you push, it won't stay with you. It will go by itself. That is, it enters the negative stiffness region here. And this is the negative stiffness. You are doing that, and it just wants to go. Everybody has this experience of the shells. If you press, it'll resist, but after a while it will go by itself to the other state. And that's what happens where this other switchback point when you're coming back. What was concave up here becomes convex up here becomes concave down. That is the bistability. And there are a lot of parameters. What is the switching force? What is the switchback force? And how much does it travel from here to there? And what is this force? What is this force? All of those. And where does it actually become unstable? All these are parameters you can control in designing these bistable elements, either arches or shells. And we can use them in many different ways. This is something that we had done with the Eaton company in Pune, where you can see it's a snap action switch. It's all a single piece. There are no joints here. When you are moving here like this, when you move this, after a while there is a delay and then it goes down and then stays there. It just accumulates energy and then snaps like this. Then moving also there is. So mechanically, you can create a delay and create very unusual nonlinear behavior for these things. This is a MCB, microcircuit breaker, but just an example of what can be done with what we call compliant mechanisms. They don't have joints. Everything is elastically flexible. It is strong. You don't have to worry about things breaking because we keep the stress low enough in these designs. So now let me come to the electrothermal bistable switch that I would like to describe to you. A little background. Where do we need this? In terms of micro actuators, RF switches are something that are very widely researched, and there's a lot of work that is going on. In fact, their performance is actually meeting the requirement that they'll be commercially used as well. In fact, some of them are already used in some devices. So here you need switching speed to be very quick and frequent. If that is the case, using thermal actuation might not be good. Then you need electrostatic, which can go to gigahertz frequency of operation. But then force will not be much to make a good contact with the switch. If it is milliseconds or slower, you can use electrothermal. And there are usually cantilever type of switches. If it is here, you have electrostatic actuator, let's say, it attracts and it will come and close the switch. But then we thought that there will be some applications. In fact, there are redundant selection in antennas where your need to switch between on and off is not frequent. Only once in a while you have to do that. So if you were to actuate to keep the switch in the on position, then you are actually consuming a lot of power. So if you only need once in a while, it's better to use the bistable design. That is, only to switch between one state to other state, you need power. After that, you don't need power. So you don't need to provide power continuously. And that's a bistable switch that I'm going to talk about. So this was funded by IISro. So these are the specifications that they had given to us, how to make this switch. And in terms of RF behavior, that I'm not a specialist. I'm a mechanical engineer. I work with people who know Professor KJ Vinay in IISc, also Dr. Giridhar, MS Giridhar at LEOS. So they do the RF modeling. And also one professor from Madurai, Professor Kantamani, is actually doing this for her work as well. I'll come to that at the end. So what we like to do is actually focus on the design now. It's bistable, also bimodal. I'll explain what that means. And then how to integrate the electrothermal actuators, and fabrication. I'm not going to go into details because fabrication today is accessible to everybody in a way, in India too. I'll come to that again at the very end of the talk. And then some testing that we have done. RF character that is done only preliminary because it's an ongoing work. And we did a comparison of our switch with others. Most people today, when you make these switches, use electrothermal actuators because they have larger force, and there are applications where the slowness of operation is not going to come in the way. And within that, there are two types of electrothermal actuators. One is V-beam, other is what is called a heat-actuator. Heat-actuator is the folded beam that I had flashed at the very beginning. V-beam is the one that I'll be talking a lot, so I will not explain that now. So many people use V-beam because it's very simple and can be very effectively integrated with the devices. Let me explain the basis for our work. It is from a paper by Hong and Yang. So where they did what is called a two-terminal bistable switch. That is, here they have one terminal and another terminal, and then this one and this one. Basically, you have these two maintained at ground. This and this maintained at ground. This and this has a potential. Then the switch would go and hit this other bistable arch. When you actuate this thing, it will go and hit this, then it will go to the other side. And then when you apply potential in the same place, it will come back. It's like those lights when you pull a cord, they'll turn on. You pull again, it will be turned off, right? In a similar way, the same two terminals, you apply voltage, it will turn on. You apply voltage again, it will turn off. Only thing is the duration of the pulse, you need to change a little bit. It's looked very interesting, but then their design was very, very far from being robust. That is, when we took this design from this paper and then tried to simulate it, it was just not switching. So we thought we should work on it, and the problem was this particular lever that they have, this was not strong enough or was not doing the intended job to make it robust to manufacturing tolerances here. We're starting with that. We used our ability to design bistable arches and came up with a design that looks like this. In the process, we had to come up with a new kind of actuator, which we called initially retracting actuator. That is an actuator, it was just going forward like this. It will initially go back and then move forward. And there is a reason for it, and as I'll explain. So our switch design is basically you have three terminals, but actuator and actuator 2 will have the same thing, that is ground and one potential. It's a normal three terminal would have two different things. Even though we have two actuators here, we have only two terminals. Between the terminal, that is this and this will be at one potential, this and this will be the other potential. And that's how we do two terminal. It makes the power electronic circuitry easy. That's what our ISRO team, LEO's people told us. And that's why we moved ahead with two terminal design. How does it work? There is use that as a amplifier. That is with little force, not little force, displacement is small, but force is high that comes here. That will make this close this gap and push this arch. And that arch will go to the other state, as we'll see now. So now you see, I'm applying force over here by closing this switch. Okay. Now that pushes this, and now this started pushing. So the switch that was there, now we break that transmission, RF transmission that is here shown with the dashed line. We break that. Of course, I'm showing slowly, but it will happen dynamically in the switch. The next step is this arch actually will switch, because we have to design in such a way that this thing, when it is pushed here, because of negative stiffness that it has, afterward it goes by itself to the state. So it goes by itself and stays there. Now the switch is off again, right? So watch again. I'm closing the switch. It pushes and goes. Switch is off. No more power consumed. And now I'm closing another RF line. There's a switching between that line and this line. Now it stays there. Okay. Now if I want to remove it, I apply voltage. The same thing again on this one and this one. I do that. Now this starts going initially that way, retracting. So this actually comes back, and then that actually moves forward. That helps it to switch back here. It comes this way. Let me play this again. So initially it is here. We actuate that, it moves down and goes back, stays there. Now I apply voltage again, and then it comes back. So I can switch back and forth by applying the same voltage but different durations. And how do you design this amplifying arch, this bistable arch? And there is a electrothermal actuator here, and there's a special kind of electrothermal actuator. All of them together give you this behavior. So first of all, I said we need a new kind of actuator here. There is this heatuator, as I called it before, that is there. It can be a V-beam actuator. The V-beam is V is this way. So a sleeping V here. So V that way. There is a heatuator. So when we want to switch it from here to there, this one should not move in this direction. When it moves in this direction, this will not be able to switch to the other side. Okay. On the other hand, when it is already there, you want it to actually go that side a little bit initially so that you can pull it back to this side. So we need an actuator that moves back and then comes forward, all in one thing. And that's what I think we have been able to do here. So normally this heatuator, when you apply voltage between these two, you bend that way. Similarly, if you have V-beam actuator, when this is at potential V and this is a ground potential, current will go through, that will cause ohmic heating to expand. This point will go that way. Now, what we want is something that goes in one direction and then comes back, goes back and comes forward. That's a behavior we want over here, and we try to do that. In other words, as time goes, it's a dynamic behavior, initially retracting. So this one goes that side, whereas this one, because the angle of this V-beam, moves this side. But then this is shorter compared to this, the length of these individual elements in the V-beam actuator. So there is less resistance for this. And so current actually goes through this and it heats up faster than this in terms of response. That's why initially this will go that way. But afterward, the force in these things is much higher than force in this. It will start going that way. That is, initially it will go down. This is the displacement. This is the time. Initially it goes down and then catches up and then goes forward. Or we can design them in such a way that it can go back and then come forward and not go beyond the original state, or can go back and come a little bit and still stay back, right? So these things initially at t equal to 0, if it is here, up to some tau in between, it will actually go back, as you can see here. Yeah. See, initially it is here. When I just actuate, in that dynamic time, it's only a few milliseconds, it actually comes back. And then you continue, it actually goes forward. This is what we call initially retracting actuator, and that's what we need for our design so that this bistable switch can go back and forth. And you can see this, how it happens. If I play this video, it's a simulation. See, initially it goes there and then comes forward. I'll play again. Initially it goes to the left and then moves to the right. It's all in design. We're not doing anything complicated control here. Okay. So here we need to do electrical analysis, and then the thermal analysis, and then finally the elastic analysis, for which you use this Michel's theorem. Again, it's Nilesh Mankame's work that he had done. So now we work on what we call topology optimization to design these things. We can do that, but then in a practical application, we want to keep the geometry simple enough. So in this case, we went to this just the bent beam actuator, did analytical modeling of that, and try to get, if we apply certain potential between these two ends of the V beam, how much does it move, what is temperature profile, and all of that. And it's highly nonlinear because we have electrical analysis first, and then the thermal analysis by taking Joule heating, taking temperature loads, you have the elastic analysis. But everything can be done analytically. We can, in fact, here using Fourier I think there is some noise somewhere. Maybe somebody has to mute the mic. Okay. So we can get this displacement analytically and try to design how many of these beams are needed, how many of those beams are needed, what should be their stiffness, and what should be the width, and what is the length of this versus length of this, and so forth. We can do everything analytically and get the appropriate things. And here again, normal actuators, force, zero displacement, it will go down like this, at least in the linear regime. Whereas here, it initially goes there, that is the negative part, and then from there it comes forward. So we have this. So this is how the energy will be in this initially attracting actuator. We also pay attention to the energy. Also model this whole thing as one spring in to design this thing, or make this the spring to design the arches. Lumped modeling basically. We do that so that we can design the actuators and the mechanism together. And then a lot of analysis here and optimization as well, where we would like to make sure that it has that snap through or bistable behavior. So the entire structure is now modeled as in the previous one, we had modeled the actuator like a spring, whereas here we are modeling the entire structure here as a spring, and to see at for what stiffness here this will demonstrate the bistable behavior. All that can be done analytically, and we can of course do finite element analysis, but for design, doing analytically always makes more sense. And also we have initial tracking actuator, we have to time it. What is that tau where it goes one direction and then starts coming back to the other direction? The tau also has to be designed properly, and we put that to 1 millisecond, and the threshold displacement to the left and right, we put those, and minimize the power required, because that is a requirement from ISRO's specification also. You should consume as little power as possible to switch, even though it's intermittent once in a while. Even then they want the power to be low. And we did all of those calculations, and try to look at the behavior analytically by looking at various energies that we have here, and then what exactly happens to the force displacement curve of the nonlinear spring, that is this entire structure. As you can see, initially itself it is nonlinear, suddenly switches because it contacts other one, goes to some level to switch it, and then it actually snaps back, this entire structure. So we can design this behavior the way we want. And we also did optimization with various parameters, length of the beam, width, and the offset between the two things that we have, between the amplifying arch and the bistable arch, and number of beams and so forth. So we did that, and this is simulation where you can see when I'm actuating now. Previously it was just a rendering, right? Now it is actually simulation. So I'll play it again. So it's now coming back slowly. Okay, so let me play from the beginning. So we actuate that comes down, and then it loses contact. The top one goes back. Now we have removed the power. It will stay there. This is off to on. Once it is here, that is here, I can apply voltage again between the same two terminals. If I do this now, it's going to switch back. So now it is slowly going, and then went there and then switches. This slowly moving is important because it moves slowly and then pick up speed and snap. Otherwise, you don't make a good contact, and that's what it is. So now actually we have fabricated. We used SOI MEMS process, and also we have made in IISc now using SOI silicon and insulator. There's a handle layer, thick silicon about 400 microns. There is silicon dioxide, which is a buried oxide layer called box layer, and then device layer 25 microns. What you see the top views of the thing that I showed, and the close-up view of the arch as well, these arches, right? And then these actuators, you see these beams, and this beam arch width is 8 microns, and the whole size of this is 3.5 millimeters by 2.2 millimeters. And we can get a number of these devices and then do the testing. Now this is a video of the real device where you can see this is the RF transmission line from here to there, and then is another one. this portion, from there it will switch back. Just watch. And this is a big probe, and this is another probe. Only two terminals. There is only one terminal, another terminal, and that's what we are doing. The big electrothermal actuator, and then these are the array of these amplifying arches, and then there is this bistable arch, this initially retracting actuator. And this has, we apply this for 200 milliseconds. In this particular video, 11.8 volts, and this is 25 milliseconds to switch off. It requires much less, same voltage, but for much shorter duration, it will switch back. So I'll play this. This is a real device. Now it's switched there, and then we apply for 25 milliseconds, then it's going to switch back. It comes back to the original position. So this demonstrates that this concept actually works, is quite reliable. Once it is in the switch state, it will stay there until you apply voltage. So small vibration, anything will not switch. That was the problem with the paper that I had talked about earlier. And this is a electrothermal actuator. It gets hot, so that temperature can actually visualized using IR imaging. And then we compared our analytical model. It predicted maximum temperature to be 80, whereas measurement was 78. And the initial tracking actuator, so this gets hotter sooner, shorter one compared to the longer one. Here measured was 148, analytical model said 153. So it's pretty close. There could be error in the measurement itself, or properties we don't know. So, but again, we wanted to make sure that our modeling is correct. And then there is this dynamic response that we need to measure. So this is done with laser Doppler vibrometer. I see Professor Suhas Mohite there, our IISc PhD student. Suhas had done some wonderful work on MEMS here. So he knows about this laser Doppler vibrometer. This is a much newer one, Suhas, compared to the one that you had used. Now we have a nano center where we have all this setup. We can actually measure this displacement dynamically. In fact, much faster than milliseconds. But this one has millisecond behavior. So we have analytical one, there is finite element analysis, the measured. They're not perfectly agreeing, right? Because there are a lot of uncertainties in the thing. One of the things is we do not consider convection because convection modeling is quite difficult. We can do it. That's what Nilesh Mankame had done long time ago. But when you're designing, getting all that complicates matters. We do this and then we measure it and then see what the problem is. One of the things that we had seen was that this was a very subtle thing that when you are modeling these individual actuators, there is some heat that goes from one to the other. Even though they're identical, there's a little bit of heat, especially in our initial retracting actuator, the shorter beams and longer beams, there is some heat exchange between them. It goes back and forth. Initially that gets hot, it responds faster than the longer one. So heat from here goes there. Later heat from here goes to this as it heats up. So we need to consider that also in our analytical modeling, and that's what is being done right now. And the next thing is RF characterization. There are a lot of requirements for this, insertion loss and isolation and other things that you need, and that was not really good. And one of the reasons was that ours is a planar actuator, not an out-of-plane actuator. Out-of-plane actuator, you have a proper metal coating on it, top and bottom, so you can switch. Whereas here, what we have are these sidewall contact, right? This particular one comes in contact. So we will need to have sidewall coating. We have done that by sputtering in our nano fab here, but that's one of the reasons why it is not behaving as well as it should for the RF performance. Mechanically, it has no problem. It switches. Now we need to get the fabrication so that sidewall coverage can be properly done. And Professor Kantamani, who is in ECE department in Tyagaraja College of Engineering, Madurai, she's under this program. Since a faculty development program, I want to tell all of you that SCRB, Science and Engineering Research Board of TST, has this program that many of you might be aware of called Teachers Associateship for Research Excellence. So Professor Kantamani applied for it and got this. This is an excellent opportunity for college teachers where you can propose a topic and come and work in places like IISc or IITs where there are good facilities, so that you can actually stay there. They pay for everything. They actually give you monthly slightly increase in salary, 5,000 rupees or something, and then consumables money, and then travel and everything for coming and working at an institution. Because Kantaman is actually doing modeling, RF modeling. Because I'm a mechanical engineer, so I need somebody who can do this. We actually doing the HFSS, a software, to see how to compute the insertion loss and isolation and other things that you need for RF performance, S parameters, and that's what she's doing. Now, I would like to actually take some time to talk about how all of you can do MEMS research. So Suhas Mohite did his PhD here on a QIP program, and that some of you might be doing already. But after you go back, you don't have to worry that I don't have a MEMS fabrication facility, or I don't have these tools or anything. So I think it can be done today. Software is available in various places, and you can write your own codes as well. And when it comes to fabrication, I would like to talk about a community chip that we run. There is a professional society called Institute of Smart Structures and Systems called IISc. And there are some foundation courses. I just finished one MEMS design course, and there was other course on IoT, and then there was a biosensors course. There are a lot of courses that IISc offers. These are all now online. They used to be in person. Now they're all online. And this community chip is something where several colleges come together. In fact, we have done already 4 times. Colleges come together and they share a 1 centimeter square chip. That's why it's a community. Everybody shares that little 1 centimeter square. You don't need a whole lot of space. In fact, if you have 100 by 100 microns, you can actually do some devices, right? And all of those are put into one chip, and the design is sent to a foundry called MEMSCAP. And they make the devices and they send you back. And then we cut them out and send to individual colleges, or they can use IISc's nano characterization facility to test them, so that actually you can do research like everybody else is doing anywhere in the world because of this. So this IISc, this is the web address, IISonline.in. There are chapters, IISc. I just want to take one moment to go to the website of IISc, so I can point out a few things. IISc has a journal, and I urge you to submit to the journal if you want to publish. It's actually a Springer journal. IISc and Springer co-published this. There's Gopalakrishnan at IISc editor-in-chief, and we have a newsletter called Sukshma. And then we have awards for students, undergraduate, masters, and PhD, Young Scientist Award, and Technology Award, and so forth. Now this is just over. Awards will be announced soon, but next year you can just keep track of IISc. And also, we have these public lectures now online, so you can attend those as well. And as I said, we have journal, but also you can become part of the community chip by becoming a member of IISc. Both for students and faculty is an excellent opportunity. And there is a chapter in Pune. Those of you who are in Bombay, you're close there, but we also have the chapters in Visakhapatnam and Madurai and Hyderabad. And more other chapters are coming at Kanpur and other places as well. So you can consider becoming a member of IISc, because that lets you actually design your devices, analyze them, and finally you can make them and characterize them so that you can also publish papers. Yeah. So I would end here and take any questions that you may have. I hope the talk was audible to everybody.
Yes, sir.
Yes,
Yes, audible. Yes, questions, please, participants.
Sir, may I ask this one question to you, sir?
Yes, please.
Yes, please go ahead.
Sir, in machine tool engineering for the damping and the vibration, how this MEMS is useful, sir? Damping and vibration in machine tool engineering, how the MEMS is useful, sir?
Yeah, if you talk about machine tools, the forces there are quite high. So MEMS can be used as sensors there more than actuators, right? You can mount these accelerometers and other strain sensors and so forth on the machine tools and sense the vibration and try to take that sense modalities and then use actuation some other way. MEMS actuator cannot do, MEMS sensors you can do, and MEMS sensors can be developed for high temperature applications also. In the, for example, lubrication you have in machine tools, and this is a very corrosive environment. Even there, MEMS chips can be put high temperature too, and people are doing that. In machine tools, having a lot of sensors makes sense, and people are doing that, but not for damping and other things. You can only sense.
Oh, okay, sir. Thank you, sir.
Any other questions?
Yes,
yeah.
Professor Ankit, Professor Ankit, you have a question, right? Yeah,
Good morning, sir.
Yeah, good morning.
Thank you for your extensive talk on this MEMS applications. Sir, basically, my question is somewhat not much related to the MEMS, but I would like to ask, actually, sir, is there any non-conducting type materials applications in MEMS?
Non-conducting materials?
Yes, sir. Is there any non-conducting type material structures are used in MEMS applications?
Yeah, there are several. I think polymer MEMS is a big field in itself, and there are also ceramics. Ceramic MEMS are also there. We use SU8 polymer extensively to make these micro robots that I showed some of those videos, right? And to make our micro grippers. So polymers and ceramics are used quite a lot, and they are not electrically conducting. And there are different applications. Yes, yeah, they're used quite a bit, and glass is also used quite a bit in microfluidics.
Okay, sir. So, how can I get this applications of that non-conducting materials? Is there any source or any book are available?
Yeah, polymer MEMS now, PDMS and polycarbonate, these things are quite well covered in the literature, including some books as well. Yeah.
Okay. Thank you, sir.
There are also NPTEL lectures you can see. There is one of our own, but there are a few others. Okay,
yes,
NPTEL lectures are there. You can find them. BioMEMS, if you take, it mostly uses polymers for
Okay,
micro.
sir. This lecture is available as per as your name or some other faculties?
NPTEL lecture that we have is actually given by 4 people. Professor Kane Bhatt, Professor Gopalakrishnan, Professor Vinay, and myself from IISc. There are others, other places also. There are quite a few NPTEL courses. Yeah.
Definitely.
Sir, in NPTEL, this MEMS NPTEL is the name of the subject that is MEMS or different names, sir?
Sometimes it could be MEMS, sometimes could be micro sensors and people microsystems. So but the keyword, if you type MEMS, I think it should come up.
This is in the first semester or the second semester?
I don't know. It is semester. It was done long time ago, almost 10 years ago. Okay, and so it's not like a course on SWAYAM or whatever now. It's just an NPTEL. Okay. And there is also a book that we have written. Several of us in IISc, 5 authors, which is published by Wiley. It's reasonably priced. So that has at the undergraduate level, because it's a multidisciplinary field, and everybody can access this. Yeah.
Okay, sir. Okay, sir. Thank you, sir.
Good morning, Professor. I have a question. Since I am from electrical field, you said that this particular electrothermal bistable switch can be used in power electronics. So in power electronics, most of the switches are used in high frequency ranges, especially in PWM or whatever may be the things. They are all used in high frequencies. Shall we use these kind of MEMS switches in high frequency?
No.
And if it is going to be, then what is the range of frequency can be used?
No, actually, the one that I described, they're not meant for high speed. Okay, this is electrothermal, can only go as fast as millisecond, not faster. But if you want to use electrostatic actuators, can be used. When I said power electronics is in the context of two terminals. We have two terminals. It makes electronic design easier, is what I was told, rather than three terminals, right? But this is meant for switching once in a while. And also milliseconds if it takes to switch to select antenna, then it doesn't matter, right? But if you have high speed, then electrostatics is the better option. But then electrostatic doesn't have a good force, so you need to pay extra care to get good contact.
Okay, sir. Okay, sir. Thank you. Thank you, sir. Thank you very much.
Welcome. Okay. Yeah, if there are no other questions, I want to actually say that Nilesh Mankame, again, your student, remembers many professors, in particular, Professor S.W. Marathi, I think he said. He's no more also, he said, but I think he conveys his regards to all the teachers at your college.
Okay, sir, sure. It's a proud feeling for us, like Nilesh, Mr. Nilesh has worked with you. Professor Prasanna Gandhi is also our alumni, sir. He is from SKC.
Oh, I see. Okay. Yeah.
Yes. I'm student of Professor Gandhi. I work with.
I see. Yes.
So thanks for your lecture, sir. You covered nicely the history of the MEMS and then this bistable switches, electrically actuated bistable switches, and also sharing the information about the IISc. So definitely the participants get the benefit of all this lecture and the information which we have provided. So thank you very much, sir, for being with us.
Yeah. Thank you for listening. Yeah.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir, for the lecture.
Thank you. Bye.
Yeah. So we have next session by Professor Prasanna Gandhi at as per the schedule. And do join the 10 minutes before to avoid the last minute. Thank you. Thank you to all.
Thank you. Bye to all.
Bye, sir. Hello. Hello, dear participants. You can leave now, and we are having next session with Professor Prasanna Gandhi, and the session is at 1:30. So you can join at 1:15. Okay. Feedback link is provided in the chat box, so you can fill the feedback. Okay. And there is no other link for the feedback. That is only one. For each session, we will have this feedback link, and attendance is monitored through automatically. So no need to panic about that. So attendance is monitored automatically. So we are taking care of it. Okay. So please join at 1:15.
And sir, one more question. Hello.
Yes, please.
And when this test would be conducted, sir?
It will be conducted at the end of the program. Like there will be 25 questions. Okay. And these 25 questions will cover the